conceptually easy, but it tends to give you writer's cramp after a while. So we find the following result. The reduced density matrix for the first oscillator is equal to m over the square root of m over pi, and of course the Gaussian integral always yields another Gaussian, and so it's 1/2 m times x squared plus x prime squared minus 1/4 n times x minus x prime, where m is equal to 1 minus mu over 1 plus mu varies, and n is equal to 4 mu over 1 minus mu squared, and I remind you mu is equal to gamma squared, although I just erased the definition of gamma. But now we know, and for this density matrix, so this is a density matrix, but we know its entropy. Its entropy is equal to minus log 1 minus mu over 1 minus mu log mu. I think that just got erased, but that's what we got before. Okay, so what we've done, we found the entropy of this density matrix, density matrix. We have the form of the density matrix in the position representation. And now we can compare it with this. So you see it has exactly this form. If I just think of M as a 1 by 1 matrix now, just a number, I hope I chose the notation, so this has exactly this form. So in the case of just two coupled harmonic oscillators, we know the entropy. We need to do a little bit, but this was so far M and N are not completely general. They're related to each other by this expression. Although so there's only one free parameter in this expression. However, notice that, so I claim, just as dimensional analysis, and you have to do a little more work to get the general entropy of the general density matrix in this form. But if you look at this, if you think of the dimensions of these quantities, both M and N are dimensional quantities because X is a dimensional quantity. But the entropy is dimensionless, so it can only depend on a dimensionless combination of that, and that has to be N over M. So so S it has to be a function only of the ratio, which I called lambda, of N over M, which in this case is 4 mu over 1 minus mu squared. 1 minus, quantity 1 minus mu squared. Therefore, this expression, this expression here, actually holds for any values of M and N if I define mu by solving this equation, if I first define lambda as N over M and then solve this equation for mu, that'll give me the entropy of any Gaussian density matrix of this form. Okay? Just by dimensional grounds. In fact,
you also didn't make that statement again. You're saying that.
Yeah, maybe I should write it out. So then I claim, this is not a claim, this is just a definition. So I claim that S was a function only of lambda. And so the claim that is in general, S is equal to, I don't know how to say it, let's give this a name. I call the other one sharp, I call this one flat. So this is the claim is that S is given by this equation flat, where mu is defined by, now we need something else, another thing, natural. This equation is natural, is defined by natural. In other words, you start with the density matrix. You start with this density matrix here. You define lambda by to be n over n. So in other words, I could say mu is defined by the equation that 4 mu over 1 minus mu quantity squared is equal to n over n. So you start with this density matrix, you define mu implicitly by this equation, and then you plug into this formula for S, and that gives you the entropy of the density matrix.
You could probably formalize that argument by making a change of variable to absorb m into x and x prime.
I'm sure I could, yeah.
Yeah.
I'm sure. Now that's the main thing we need, but it's just for convenience, it's nice to rewrite. Let's actually do this. It's nice to make a further change of variable. If we solve this equation, we get mu is equal to 1 plus lambda square root minus 1 over 1 plus lambda square root plus 1. And so we see that mu, you see, I won't prove it. If you go through and see, if you go back and see what m and n really were, I think they got erased. Did they get? Oh no, here they. Yeah, here they are. So if you go through and see what m and n really are, you will see that that lambda belongs to the. It's a positive. Or it's a non-negative number, and mu is in the interval 0, 1. So it's convenient to introduce a new thing, which is mu, which is equal to 1 over 1 minus mu. This is just sort of massaging the formula to make it look a little nicer. Which is the square root of 1 plus lambda plus 1 over 2. If you work that out, mu belongs to the range 1, infinity. So it's a positive number greater than or equal to 1. And in terms of that nu, S has a slightly nicer form. It's equal to nu log nu minus nu minus 1. So this is the definition of S in terms of, this is S in terms of nu, this is the definition of nu in terms of lambda, and this is the definition of lambda, and this is the definition. This is the definition of m and n. So we take any density matrix in this form, compute lambda from it, plug it in, get nu, and then the entropy of that density matrix is this. In fact, you can easily check, I won't bother. This has a simple interpretation in terms of the excitation number of this first oscillator. Nu is actually in the thermal state. Is simply equal to the expectation value, the mean excitation, the mean occupation number, plus 1. We don't need that as such, but it's sort of it helps in thinking about what it actually is. And so you may have run across this. It means that in the thermal state of a harmonic oscillator, the entropy has a very simple form in terms of the mean expectation number. It's just n plus 1 log n plus 1 minus n log n. That's a form that I can remember. I could never remember all this without looking them up or re-deriving them again. So we're almost done. So now all we have to do is invoke this other result that told us that we could diagonalize simultaneously any two symmetric matrices, one of which is positively definite. And that's the situation we have here. This one is always positive definite. So you can see, n could be 0, for example. If I had started with going back to the original problem, if I had started with 2 uncoupled harmonic oscillators in their ground state, then there'd be no off-diagonal terms in the density matrix. And so n would be 0, and so mu would be 0, but m will always be a strictly positive number. And you can prove that. I think I pointed it out at the time when we derived this equation, just by explicitly, just from what m and n, from this fact here, because w is positive definite, m will be positive definite. And in fact, you can convince yourself more generally with a little work that anything of this form or of this form, and let's look at this form, that m must be, in order for this to represent a valid density matrix, m must be strictly positive and n must be positive, not negative. That's because if one of those fails, I mean, in order for this to be a valid density matrix, first of all, it has to be positive in the sense of an operator. That's a somewhat subtle thing. But at a very minimum, it has to be normalizable. So, for example, if I made m negative here, I would get some divergent. When I tried to normalize it, I'd get some divergent integral. So you can see that m has to be positive. And I think you probably have to use the positivity as an operator. And then you can show that m has to be non-negative from that. So that's the result for one degree of freedom. Let's generalize it now to n degrees of freedom, and then immediately we will immediately apply to our reduced density matrix for the system of coupled oscillators. So now we generalize to n degrees of freedom. We consider now something which has the form rho of x prime is some constant times e to some quadratic expression as usual. I don't know if I actually have to write it down because it's already written down here. So there we go. The only thing is I somewhere along the line switched the notation from q and q prime to x and x prime, but it's exactly the same thing. So now, if we simultaneously diagonalize m, a, b, and n, a, b, then it splits into just a decoupled set of one-dimensional problems. In other words, after we diagonalize them, we'll have a new set of variables, x1, x2, x3, and so on. And the density matrix won't mix them. In other words, it'll look like this. It'll look exactly like this for x1 plus another term for x2 plus another term for x3. And that means that the entropy will be, one could say this slightly slightly less hand waving, but it's only a little hand waving to say that implies that the entropy, if you think about what it means to diagonalize such a matrix, then it means that the entropy will just be the sum of the entropy of the individual one degree of freedom matrix. What we're dealing with is a density, at the abstract level, what we're dealing with is a tensor product of density matrices. The entropy of that tensor product, because entropy is a log, basically, is the sum of the. But it's somehow a familiar fact about entropy. You have non-interacting systems, non-decoupled systems, and the entropy of the ensemble is just the sum of the entropies of the individual ones. So you can justify that just from pure mathematics, if you like, but it's physically completely obvious once you're used to the general facts about entropy. And so we find that S is the sum over lambda of what I'll call S lambda, where lambda is in the spectrum. In other words, it varies over the eigenvalues of this matrix lambda AB, which, did I define lambda AB before? I think maybe, I'm not sure if I did, but where lambda AB is the following. Remember, it was M. Here it was n over m. So in a matrix that after I've diagonalized it, that just means m inverse times n. Right? And I've defined m inverse to be m. I'll define this to be m inverse. And so then, and once this is diagonalized, this is just a calculation with diagonal matrices. So it's just for each value of the index, this is just n over m. So we're the stated definition of m. So MAB is the inverse of the lowered m in the sense reduces delta AC. Okay, so is it
This
clear?
is what you call tilde.
It will become tilde, yes. So far I haven't, there's a,
Again, you
this will be a W, when I substitute what m is in terms of W, it'll become equivalent. This is so far a completely general formula for every density matrix of this form, no matter where I got m and n from. So there's no tilde. This is the whole matrix. There's no.
capital A, capital B.
This is the whole one. Well, it's not capital. Yeah, you can use whatever notation you like. But this is the whole matrix. But when we come, if we just write a density matrix of this form, it's the whole matrix. When we come to remember that that represented only a block of oscillators out of the whole set, then I'll immediately substitute m to be W tilde. So that, in other words, it's almost no work. Okay, so this is writing it this way, what it means is that I take all the eigenvalues of all the different one-dimensional problems into which this is split, and I add up the entropys of each one, which was given by this expression here. And that's the answer. So I could write it out again, but I think I'm going to summarize in a second, so let me save a little time by not writing everything out 3 times. I'll just write them out twice. So this is the answer for n degrees of freedom, and now we just apply it to our reduced density matrix here, which means no more than just remembering what MAB and then AB were. So anything else I wanted to say? Okay, no more. So this is the formula, so let's now apply it to space group. Let's apply it to that special case. So that's a very short calculation where we'll use another one of those general facts that I recalled for you. So when we applying it to that just means to remember what M was. MAB was W tilde AB. And NAB, I'm just writing what's over there, was WA alpha, W tilde alpha theta, W beta D. Let's remember what this. Let's remember what this means. The definition. This W tilde is now not the whole matrix anymore. It's just the block out of it's just the Raman oscillators. It's defined so that if we invert it, we get the Raman block of the inverse of W. So what it means is that, remember I defined MAB. This may look a little confusing, but if you just write it out for yourself, it's completely straightforward. I defined MAB in this formula here as just equal to the inverse of the lower MAB. So this upper MAB, which is the inverse of the lower MAB, is the inverse of this W tilde AB. But the inverse of W tilde AB is by definition WAB. In other words, the Roman block of the inverse of the full W. Okay. And then I can substitute everything in and get what is lambda in terms of W, which is in terms of the square root of V, the original potential energy matrix for the coupled harmonic oscillator. So lambda CB is equal to M, where is it here, MAC, oops, see I've switched the letters, so it's MCA, and AB. MCA, we just saw, was WCA, and NAB, there it is WA alpha, W tilde, alpha beta, W beta B, hopefully. Now put these two, now one of the general facts I told before, which just comes from the fact that the octi, well, just look what it means that this is the inverse of this. If we sum over all indices, we have to get 0 because this is a Roman and this is a Greek index. So this is equal to minus, the sum over the Greek is equal to minus the sum over the Romans. Oops, I better give this another name. C gamma alpha. Right? But now if we take these two together, now let me just write it out. So it's equal to minus WC gamma, W gamma alpha, W tilde alpha beta, W beta B. And now look at this, if it's legible. W tilde alpha beta is by definition the inverse of the Greek block of W. So this thing just becomes delta gamma beta. And so the net result is that this lambda CB is equal to minus W C gamma W B, let's call it beta, minus C beta W beta. So it may be been a little hard to follow, but notice there was nothing tricky, except that, you just had to use the general, just use the general facts that we know that relate to this. It's not a trick, like at one point I did actually make a sort of trick using those general facts. But this is just plugging in and following your notes. So this is the main result, just to restate it. Lambda AB is equal to minus W A alpha W alpha B. Notice that it's made from the off-diagonal parts of W. So it shows you see immediately that had there been no coupling between the two blocks of oscillators, you'd get no entropy, because this would be 0. Because this coupling represents off-diagonal Greek Roman components of V. W, if there's no such in V, there's no such in W either, which is just the square root of V. So this directly shows how the coupling between the two blocks gives the entropy. So let me just, I was going to make another comment, but I'll skip it. And I'll just summarize what we found, and then if there's a couple of minutes left, I'll start on maybe the intuitive explanation of the area.
Should we have time for questions?
Oh, if you want time, okay, let me just summarize it and then we'll take questions. try. Well, as usual, it looks like I probably won't finish the whole plan now, but at least I hope to finish the intuitive experience. That's probably the more memorable part. I did want to also introduce this nice mathematical physics problem. Anyway. Okay, so let me summarize what we found so far. Then we want to apply it to the quantum field theory if we get far enough. It was an interlude of sort of some general remarks, intuitive remarks on the area law, and especially the need for a cutoff in order to get in the continuum case. So here's the summary of everything so far. We have two sets of oscillators. Simple harmonic oscillators, which we've labeled by A and alpha in the ground state. The Lagrangian for that is written as 1/2 G A B Q dot A Q dot B minus 1/2 B A B Q A Q B. W is defined as the square root of V with respect to, or relative to GAB. So in particular, it means if you choose a basis in which G is just the identity matrix, then you're just taking the square root in the ordinary matrix sense. It's a positive square root. WAB upstairs is just a capital again, is just defined as the inverse of the original W, one with the downstairs indices. Lambda is defined as minus W A gamma W gamma B. Of course, I could repeat at this point that I'm always assuming the summation convention, so that all these formulas obviously means summation. In this case, it's a summation of the Greek indices. It turns out that lambda, then we define lambda. Notice, the comment I was going to make that I skipped through lack of time is, notice this lambda itself is not a symmetric matrix. Nevertheless, if you trace through where it came from, you can see that all of its eigenvalues will be real and positive. And there's a nicer way of saying that, but I'll just skip it. But it's not, we do not claim that W is a symmetric matrix. Lambda ranges over the spectrum that is the set of eigenvalues of the matrix lambda. And all of these, as I just said, are positive real numbers. For each one of them, we define nu as nu of lambda, which is lambda plus 1, plus 1 again, square root of lambda plus 1 over 2, and then S, finally, is the sum over all these lambdas, or now it's the sum over the nu's, of nu log nu minus nu minus 1, nu minus 1. So that's the summary. That's everything that we've done really so far. And I'll just make one more remark. The derivation, by the way, I think you'll agree the derivation was almost completely straightforward. Although, if you're not familiar, for example, with Vogel-Dubov transformations, then there was a little bit of trickery in computing entropy of the Gaussian density matrix. And in getting this nice simple form for the answer, It just depends on W directly. There was a little bit of trickery in one or two places. But essentially, it's the most straightforward thing you could have done. And then I wanted to make one more remark.